Thank you for coming to my presentation. My name is Ayase Kawamura, and I'm from Hiroshima University, Japan. So in my presentation, I will talk about the self-propulsion of 3-phenylpropionaldehyde droplets. And let's start. Let's start from introduction. So the droplet system, which is composed of water and droplets, is very notable to study because this is non-living components, but they behave like life-like properties, such as compartmentalizations, metabolism, sensory taxis, and etc. And it is and this is very important to study because this has the ability to utilizing droplet systems as cellular models. And as an example of droplet system, there is self-propulsion of droplets. When the droplet system has the interfacial tension gradient, the droplets is spontaneously moving on the surface of the solution or in the solution. Sometimes it's surfing on the solutions, and it is sometimes swimming in the solution. And my research is focusing on this self-propulsion to by droplets and surfactant combination to make this self-propulsion. And another example of droplet system is a reaction. Metabolism is a kind of reaction, and if there is an example that the droplets get fuel and react it to make waste and get energy by the fuels. So as my research purpose, I would like to make the droplet system as adaptive system. And firstly, I will do droplet systems with propulsion, the self-propulsion, and after that, I will combining propulsion and reaction such as metabolism. By contributing to these two propulsion and reaction system, we can make more lifelike systems. Here is experiment. So this is the chemicals for this system. I use the droplets with 3-phenylpropionaldehyde, which is aldehyde. And in the solution phase, I use SDS or the combination between SDS and histidine, which is amino acid. And there is 3 types of experiments I did, and and first is the propulsion one, and the second is the reaction to make reactions, and the third one is the combination between propulsion and reaction. This is the experimental setup. I use the channel with 1.0 centimeter times 10 centimeters to see the droplets movement from the side. And here, now let's move to the results. And when we put 3 ppA on the surface of the SDS solution or on the bottom surface of the glass surface of the solution, the 3 ppA could move spontaneously. And to see the flow, I put the tracer particle and visualize the flow near the droplet, and we could see this kind of motion, on the surface of the solution motion, and this kind of motion on the glass surface, like circling one. And so to see the flow, I make this flow analysis and trace the motion of tracer is from red to blue, and we can see these kind of flows on the surface of the solution and the glass surface of the solution. Okay, so this is the discussion of mechanism of the movement. Now, what we know is first is Marangoni convection is occurring around the droplets that we could see from the flow visualization. And the next is 3 ppa droplets size was decreased over time. We can see from 0 hour to 1 hour. So from these two results, I made this discussion. The reason why the 3 ppa is moving is firstly, the SDS droplet dissolves, SDS dissolves a part of 3 ppa, and the formation of microemulsion is occurred. And second is dissolution induces interfacial tension gradient. And finally, this interfacial tension gradient induces the 3 ppa droplets motion. Okay, this is the summary of the first part. Firstly, the 3 ppa drop motion was observed both on the solution surface and glass surface. And SDS dissolves part of 3 ppa and induces interfacial tension gradient. And this interfacial tension gradient moves 3 ppa droplets. And next is about the combination between propulsion and reaction. Okay, firstly, I examined the reaction with 3 ppa. So when 3 ppa is attached to histidine, which is amino acid, the 3 ppa goes to oligomer. And we could see that there is white turbidity when the 3 ppa and histidine is connected to each other. And this is caused by the 3 ppa oligomers. Then, utilizing the reaction, I put the reaction and propulsion together and see the difference between the normal propulsion one and the combination of reaction and propulsion. And in case of the solution surface motion, the droplets is moving back and forth. And in the glass surface, the 3 ppa is moving with, it is very difficult to see, but sometimes it making the white turbidity around the droplets. So this is the combination between the propulsion and reaction. Okay, to see the motion with the trajectory, we could see this kind of difference between the propulsion one and propulsion and reaction combination. The purple one is the movement on with the histidine, which is the reaction one, and the green one is the normal propulsion without histidine one. So in case of the solution surface movement, with histidine, the oscillation is occurring in the solution surface motion. And in case of glass surface motion, the longer lifetime was observed with histidine by the reaction. And the next is the droplet size reduction. The same is the same. The solution surface motion. The purple one is with histidine, and the green one is without histidine. And we can see that the droplet size reduction was suppressed in case of the 3-PPA is moving with the histidine and SDS solution. And in the case of glass surface, the suppression is more occurred than solution surface. Okay, this is the discussion of the second part, the cause of longer lifetime. So by the reaction, we could see that the longer lifetime of 3-PPA droplets movement, this is caused from the suppression of 3-PPA dissolution by histidine. The mechanism of moving is the dissolution of 3-PPA into the solution phase by SDS. But in case of the with histidine, the histidine make the surface of the 3-PPA to be oligomerized and suppress they make the membrane-like structure, and this membrane-like structure is suppress the dissolution of 3-PPA into the solution phase. Okay, this is the summary too. Firstly, the spontaneous emulsification. This is a reaction was occurred between the 3-PPA and histidine. And this reaction is derived from the Holmos reaction. And the addition of histidine, like adding the reaction, caused the onset of oscillation and longer lifetime. And longer lifetime can be attributed to the formation of membrane-like structure. Okay, this is the conclusion. When 3-PPA, this is aldehyde, and histidine is amino acid, we combine aldehyde and amino acid, and together with surfactant, it could be like life things. And thank you for attention.